Okay, a couple more topics here so that we can wrap up this chapter. Ionization energy trends and electron affinity trends. What do they mean? Let's first focus on ionization energy. The first ionization energy is the minimum energy needed to remove the highest energy or outermost electron from the neutral atom in gaseous state. So you have to think of your elements and see which ones would it be the easiest to pluck an electron away. Okay. The further the electron is from the nucleus, the easier it's going to be. So as you're going up a group, the furthest electron is getting closer and closer to the nucleus, so it's going to get harder and harder. So the more energy that is required to pluck an electron away, the higher the ionization energy. So as you go up a group, ionization energy goes up. And we're just focusing on the first ionization energy, the removal of just the outermost electron. So if you look at a group, for example, cesium, compare it to lithium, lithium's going to have a higher ionization energy than cesium. Cesium, it's one electron in its outermost shell, that 6s1, so far away from the nucleus, really easy to pluck it off. Lithium, it's a 2s1 closer to the nucleus. You're going to need more energy to take it away. Okay, now as we go across a period, what's going on? Well, think about this. Non-metals over on this side of the periodic table, they don't want to give up electrons. They usually gain electrons. Remember, it's the metals that give up electrons. The non-metals like to gain electrons. So it's going to be really hard to pull an electron away as you get into the non-metal area. So as you go this way, ionization energy goes up. It's coming harder and harder to pull it away. Okay, so if you've got a list of elements, who's going to have a higher ionization energy? Fluorine or lithium or cesium? Well, fluorine's going to have a much more difficult time letting go of an electron. Fluorine wants to gain electrons, not letting go. So fluorine has a higher ionization energy than lithium, which has a higher ionization energy than cesium. Okay, so that's that concept over here. What is electron affinity? Well, think of electron affinity as the negative. See, the delta H is a negative sign, but then the more something is has electron affinity, it's a negative of a negative, it becomes positive. Okay, so the energy change obtained when the neutral atom picks up an electron. If you have a large positive value, because remember, negative of negative is positive. If you have a large positive value, it means that the negative ion is very stable. That means it really has an easy time picking up an electron. So it's pretty much the opposite of what we were just talking about with ionization energy. Who has an easy time picking up an electron? These guys over here. What about these guys over here? No, not at all. So as you go across a period, you're going to see bigger and bigger electron affinity positive values. There's a table in your book. This is table 8.4. You do not have to memorize it at all. But you can see here that if you look at fluorine, fluorine has a value of 328, positive 328, while lithium is positive 60. Much bigger positive value means higher electron affinity. All right, so again, take a look at the table. You'll get a feel for the trends, but in general, that side of the periodic table, the ones that exist as anything that likes to exist as a negative ion, is going to have a big positive electron affinity. Anything that prefers to exist as a positive ion is not going to have a very large electron affinity. Okay, good. So those are the two terms I wanted to cover. And then the last section on our what you need to know list says, understand periodicity in the main group elements. So I'm just going to go through some key things here. I just printed out the PowerPoint that I used to use sometimes. What do I need you guys to know? Group 1A, those are your alkali metals. Know the term alkali metals. They're the ones with the largest atomic radius in the period, right? We already talked about that. They tend to form +1 ions. We know that. They react pretty violently with water to form hydrogen gas. All right. So again, it's something in the displacement reactions where you've got, for example, a sodium plus water. The sodium will hook up with the hydroxide and form hydrogen gas. So this is typical reactions of group 1A, which are called the alkali metals. Okay, yeah, balanced equation and everything. All right, that's what you need to know about group 1A. +1, we already said that. They're all metallic. And I'm just going to hang up here for a second because I want to finish this video and I will call them back later. Okay, the second group are the alkaline earth metals. That's group 2A. Group 2A. These are the alkaline earth. Okay, those are beryllium, magnesium, calcium, strontium, barium, that bunch. Remember, group 1A, they form +1 ions. Group 2A form +2 ions. They are diamagnetic, right? They have no unpaired electrons. They're metals also. These are metals, these are metals. They also react with water to form hydrogen. Not as violently as group 1A, but they do that. They call it the closed S shell configuration, meaning that S is S2, it's closed, no unpaired electrons. Okay, the transition metals, which ones are those? That's this D zone over here. All of this is the D zone, okay? They have lots of different charges. They have variable charges. We know that. They are metallic also. So this is the transition metals. I thought I was just going to talk about the main group, but apparently I have this in here. They have variable charges. Okay, but you know which ones don't have the variable charges. Remember, zinc, cadmium, silver. Those are the 3 in the transition that have fixed charges. Okay, group 3A. These guys are also metals except for boron. Boron is a semi-metal. And most of group 3A, so group 3A, metals, except for boron. Boron is a semi-metal or a metalloid. And usually group 3A are +3. Usually that's the case. Commonly +3. Okay. Group 4A, that's carbon and silicon and those guys, those mainly form covalent compounds. So we're not going to write +4 or anything like that. Group 4A, they like to form covalent compounds. So group 4A, they like to form covalent compounds. Covalent molecular compounds, not ionic compounds. Okay? And their oxidation numbers vary from +4 all the way to -4. Remember when we did redox back in chapter 4. Okay, group 5A. Which ones are those? Oh, that's your nitrogen and phosphorus and arsenic. Group 5A, you can have, it's interesting, group 5A, you can have metals, you can have metalloids, and you can have nonmetals like nitrogen and phosphorus. Those are nonmetals. And arsenic, metalloid or semi-metals. And then antimony and bismuth, metals. So you can have all three different things here, metals, metalloids, and nonmetals. And different charges. You've got bismuth and antimony as metals are going to be positively charged, and you've got the nitrogen and the phosphorus, nitride, phosphide, arsenide, those would be negatively charged, and they'd be -3. All right, so fill that out for group 5A. Group 6A, that's your oxygen and sulfur and selenium. Those are nonmetals, and they tend to be -2. So 6A, they have -2 ions. We know that. And they're pretty reactive. They will react with a lot of the alkali metals and alkaline earth metals. All right. The halogens. The halogens are group 7A. The halogens, group 7A, they form -1 ions. This is called the halogens. Okay. They all form diatomic molecules. Don't forget that. Diatomic, like oxygen, nitrogen, hydrogen form diatomic molecules, but then all the halogens, you've got fluorine, chlorine, F2, Cl2, Br2, I2. The most reactive of the bunch is fluorine. Fluorine and chlorine are gases, diatomic gases. Bromine is a diatomic liquid, and iodine is a diatomic solid. Okay, and then we've got the noble gases: helium, neon, argon, xenon, radon, oganesson. They are not diatomic, they are monoatomic, and they are diamagnetic. They don't have any lone pairs. They have everything's paired up. They don't have any unpaired electrons. Not lone pairs, forget I said that. They don't have any unpaired electrons. Everything's paired up. So they've got a closed shell, and they're not very reactive at all. You're going to see in the next chapter that the heavy noble gases can form bonds, but the helium and neon, argon hardly ever do much of anything. Okay, and that is it for chapter 8. Chapter 9 is next, and we'll be learning how to do Lewis structures and formal charges and a whole bunch of other really cool stuff. Okay.